Illustration 1. A capacitor of capacitance C is charged by connecting it to a battery EMF E. Find the heat produced in the circuit during charging. Let R be the net resistance of the circuit. During charging, the charge on the capacitor varies, as we know Q is equal to Q naught into 1 minus e to the power T by RC, where we know what is Q naught? Q naught is equal to E into C. Here the E is the EMF of the battery. Current I will be dq by dt. So let us differentiate it. D by dt of Q naught 1 minus e to the power T by RC. So I is equal to E by R into e to the power minus T by RC. Coming to thermal power, dH by dt, that is nothing but I square R. So we know the value of I, so we can substitute here I square R. So square this and substitute. H is equal to integration I square R dt, that is equal to E square by R square into R into integration 0 to infinity e to the power minus 2t by RC into dt. Integrating, H is equal to E square by R e to the power minus 2t by RC divided by minus 2 divided by RC from 0 to infinity. Or this value can be taken up, E square C by 2 times of e to the power minus 2t by RC from 0 to infinity. Or we can write this as half of E square C into 1 minus 0. So the total heat developed in this case, heat produced in the circuit during charging will be half of E square into C. This will be the total heat produced during the charging. Illustration 2. In the electrical circuit shown, find the reading of ammeter ideal just after closing the switch and long time after closing the switch. So this is a battery connected. We have resistance here as R, resistance R, this is 2R, this is the capacitor C. When the switch is just closed, the capacitor will behave like a closed switch. The circuit just after closing the switch and long time after closing the switch, we can separately draw and work it out. So this circuit, suppose just after closing the switch, will repeat. Just after closing switch. This capacitor which was placed here, we have taken it out because the capacitor behaved like a closed switch. So when this capacitor is short circuited, so this resistance 2R is short circuited because this point and this point will be at the same potential. So resistance R and this resistance R will come in series. EMF is E. So what will be the total current I naught? I naught will be equal to the total EMF by Ohm's law divided by the total resistance, that is R plus R. So this will be E by 2R because here the resistance 2R is short circuited. So the reading of the ammeter will be I naught and I naught is equal to E by 2R. Similarly, long time after the switch is closed, how does it look like? Capacitor is fully charged. So it doesn't allow any current to pass through it. So it's like a broken circuit. So here the capacitor does not conduct any, it is in steady state. As capacitor does not conduct at steady state. So this will be a broken circuit. So because of this, these 2R resistors will come in the circuit now. R, 2R and R will be in series. Total EMF is E. So we can calculate now the current as I naught, or I after long time after connecting will be EMF E divided by resistance R. This is 2R plus R. So altogether E by 4R. This is when the switch is connected for long time. So when the switch is connected for long time, this capacitor will be as if it's not existing, doesn't allow any charge to flow or current to flow. Therefore, this 2R resistor will now come in the series with resistance R and R. The ammeter reading will be E by 4R. Illustration 3. Find time constant of the following RC circuit. Now this is RC circuit with resistance R, the battery is positive negative R2 and the capacitor C. When we have to calculate the time constant can be written when more resistors are there as R equivalent into C, RC. So to do this, to calculate R equivalent, short circuit the battery, redraw the circuit by replacing the battery by a closed 0 to T. Find equivalent resistance across the capacitor in each case. So this circuit I have redrawn with battery replaced, and a circuit is replacing the battery here, short circuited. Resistance R, R2, and across the capacitor we have to calculate equivalent resistance. So when we want to calculate across capacitor equivalent resistance, since it is replaced by an ordinary wire here, this resistor will be short circuited. It will not be existing in the circuit. So only resistance R2 will come across this. So the time constant tau will be equal to R2 into capacitor C. This is the time constant of this particular RC circuit. Illustration 4. Find the time constant of circuit when S is closed. Similarly, when S is open. So we will follow the same path as we have done here. The time constant is given as tau is equal to R equivalent into C. To calculate R equivalent, first short circuit the cell and replace the cell by a closed path, followed by find equivalent resistance across the capacitor. So in the first case, when the switch is closed, we'll replace this battery with an ordinary wire. Across this capacitor, we'll try to calculate equivalent resistance. R1, R3 resistor will come in parallel, and that will be in series with R2. So R net will be equal to R2 plus R1, R3 divided by R1 plus R3. So tau will be equal to R2 plus R1, R3 divided by R1 plus R3 times of C. This is the time constant of the circuit when switch S is closed. Now when the switch is open, let us do the same. When the switch is open, this circuit is not there. Since there is no cell, we can directly calculate the equivalent resistance across the capacitor. So R equivalent across capacitor will be R2 plus R3. So tau will be equal to R equivalent into C. So in this case, time constant when the switch is open is R2 plus R3 into C. So when switch is open, this circuit won't be coming into the circuit. So across capacitor R2 and R3 will take it up, and then we calculate the value of R net or R equivalent and then calculate the time constant. Illustration 5. A charged capacitor C1 is being discharged through a resistance R by putting the switch in position 1. When the discharging current reduces to I0, switch is suddenly shifted to position 2. Calculate current I through the circuit as a function of time. Initially, C2 is uncharged. So here we are taking a charged capacitor C1. Just before shifting the switch, let us take the current flowing in the circuit reduces to I0. So current in this circuit is I0. Half of the circuit shown here at the instant we can use Kirchhoff's law or voltage law. So let us call this current as I0, the current flowing in the circuit. This is switch 1. This capacitor is fully charged. At this instant, the charge on the capacitor we can consider as Q0. So using Kirchhoff voltage law, in the circuit A, B, C, D, back to A, what do we get? Minus I0 R plus Q0 by C1 should be equal to 0. So Q0 will be equal to I0 R C1. This is the charge at this instant on the plates of capacitor. And what is the voltage? V0 will be equal to Q0 by C1. So this will be written as I0 into R. Therefore, at this instant the switch is shifted here. So we will take a t is equal to 0 when the switch is shifted to position 2. We can call this particular potential difference as called the initial potential difference, and this charge as the initial charge. Therefore, the initial potential difference across C1 is V0, that is equal to I0 R, and initial charge is Q0. And what is Q0? Q0 is equal to I0 R C1. Now from here on we start the problem. Now the switch is shifted to position 2. Now when the switch is shifted to position 2, the sharing of charge take place between C1 and C2. Flow of charge will take place until the two capacitor acquires common potential. During the process, there is a loss of electrostatic potential energy of the capacitor, which should appear as the heat energy in the resistor R. When the switch is shifted to position 2, sharing of charge takes place between C1 and C2. Flow of charge takes place till the two capacitors acquire common potential. During the process, there is a loss of electrostatic potential energy of the capacitor. This appears as heat in the resistor R. Heat produced, we know delta U, we have the formula for the capacitor C1 C2 divided by C1 plus C2 times of V1 minus V2 whole square, where V1 and V2 are the initial potential difference across the two capacitors. What is V1? We know I naught R. What is V2? 0. Let us substitute. Heat produced will be half C1 C2 by C1 plus C2 into I naught R minus 0 whole square. So finally, the total heat produced will be I naught square R square C1 C2 divided by 2 times of C1 plus C2. Now when the switch is thrown to position 2, we want to calculate what is the charge on the capacitor as a function of time. We have to calculate the current through the circuit as a function of time, and initially capacitor is uncharged. When the switch is thrown to position 2, C1 get discharged, C2 is getting charged. Let at any instant I is the current flowing in the circuit. Current flowing in the circuit is I. The charge on the capacitor C2 is Q, and the charge left on the capacitor C1 is Q naught minus Q. Now using Kirchhoff's voltage law in the circuit A, D, E, F. Remember I is equal to dq by dt, the rate of charge increase on capacitor C2. So let us use it. Q naught minus Q divided by C1 minus Q by C2 minus I into R across resistor is equal to 0. We can readjust and write Q naught by C1 minus Q times of C1 plus C2 divided by C1 C2 minus I is equal to dq by dt times of R is equal to 0. So we can integrate bringing all dq terms together. 0 to q, dq divided by Q naught by C1 minus Q times of C1 plus C2 divided by C1 C2 is equal to integrate dt by R, which gives us minus 1 by C1 plus C2 divided by C1 C2 ln of Q naught by C1 minus Q C1 plus C2 divided by C1 C2 from 0 to Q is equal to T by R. Let us simplify this. We get it Q naught by C1 minus Q times of C1 plus C2 divided by C1 C2 whole divided by, after substituting the limit, Q1 by C1 is equal to e to the power minus T C1 plus C2 divided by R C1 C2, which on simplification we get it Q C1 plus C2 divided by C1 C2, that is equal to Q naught by C1 to 1 minus e to the power T C1 plus C2 divided by R C1 C2. So the charge on the capacitor C2 will become Q naught C2 divided by C1 plus C2 into 1 minus e to the power T to C1 plus C2 divided by R C1 C2. Now since we require the current, I is equal to dq by dt. So Q naught C2 divided by C1 plus C2 into C1 plus C2 divided by R C1 C2 times of e to the power minus T C1 plus C2 divided by R C1 C2, which gives us I is equal to Q naught by R C1 e to the power minus T C1 plus C2 divided by R C1 C2, or I is equal to I naught e to the power minus T C1 plus C2 divided by R C1 C2, where I naught is equal to Q naught by R C1. Since we have calculated Q naught is equal to I naught R C1. This is the initial charge on the capacitor. So maximum current at that instant is I naught. Replacing I is equal to I naught e to the power minus T C1 plus C2 by R C1 C2.